How's it going? This is Mr. Murray coming to you with a video on the Course 1 Honors Do Now. This is our Do Now for March 19th, 2020. Okay, so for this Do Now, what we're going to do is we are going to talk about factoring completely. Okay, so please make sure before you proceed with this, and this should be in the lesson notes for this day's class, please make sure that you've seen the lesson for 318 2020. Okay, so at this point, we've had a couple lessons. On 316, we talked about factoring, basic factoring. Okay, so A was equal to 1 generally, and I started to talk about some interesting patterns with special cases. On 317, we talked about maybe intermediate factoring. Intermediate factoring. So we'd had, for example, usually A was more than 1. And in 318, we talked about what I called it like factoring 3 because it was the third lesson on factoring, and this was special cases. So we talked about difference of squares, we talked about perfect squares, and we talked about greatest common factors. So please make sure before you proceed with this Do Now that you, one, understand the three types of greatest common of special cases. That is greatest common factors, that is difference of squares and perfect squares. Please make sure you understand those. Okay, please make sure you understand the ideas behind factoring, that is using the box backwards. Okay, and then try this Do Now. Try to factor completely, which means taking out any greatest common factors. So for example, if I had 2x plus 4 x minus 3, this would not receive full credit because you need to take out the 2. This becomes x plus 2. Okay, so this is factored completely, and then finding the x-intercepts. And it should be a point where I have an x value and 0. So here it would be negative 2, 0, 3, 0. Okay, so go ahead, and by the way, if you're wondering where this came from, I just made this up just to give you an example of factoring completely, so don't worry about that. Okay, so go ahead, take a moment, pause the video, try to factor each one of these completely, finding the x-intercepts, and then when you're ready, unpause, and I'll show you how to solve it. All right, so here we go. I'm going to head down, and let's try to tackle these. So these are all actually three types of special cases. This is a perfect square. This is a difference of squares. And this is a case where I have a greatest common factor. Okay, so as I talked about in the 318 video, if you don't remember the perfect square formula, it's not the end of the world because you can always use the box. So the perfect square formula, what it does is it helps give us intuition, and it helps make the process of narrowing down our possible things that we need to place when we factor a little bit easier, right? So as we've hopefully seen by this point, and if you have not seen this, you really need to go back and look at the 316 lesson, is that our biggest power of x goes in the top left, whereas our number goes in the bottom right. So this becomes an x, this becomes an x, so I get x squared. And now I need to get 49. And so what I notice, right, is I notice that, well, first of all, 49 is a perfect square. 49 is 7 squared. This, right, is x squared. And also I notice that when I do 7 times 2, I get 14. So let's try 7 and see what happens. And so when I do this, what I get is I get 7x and 7x. So these add up to 14x. So I have x squared plus 14x plus 49. Meaning my factors are x plus 7 and x plus 7. Or in other words, x plus 7 squared. If the factors are repeated, you do need to convert it to a square for full credit. That is important, and it's not insignificant. And by the way, you might notice this is actually in vertex form with a vertex of negative 7, 0. Okay, and if I want the x-intercepts, if I plug in negative 7, what I get is 0. So that's my only x-intercept. This is actually an x-intercept and the vertex. Okay, because when you have a perfect square like that, that is usually what's going to happen, is your x-intercept will be also the vertex. Notice that we can see it's a square because the length is x plus 7 and the width is x plus 7, and a square always has the same length and width. Okay, and the next one, what we have is a difference of squares. So you might notice that 3 squared is 9. You might notice that x squared is x squared. And then whenever you see the situation, you want to look at the other number and see, is that a perfect square as well? If the first one is, it's worth trying to see if the second one is. And since we have a difference, right, the difference of squares is possible. As it turns out, 256 is 16 squared. So if I'm going to do my difference of squares, it's going to be 3x minus 16 times 3x plus 16. And you can see if I was going to box this out, I would get 9x squared. I would then get 48x. Then I would get negative 48x. So 48x minus 48x, so they cancel. And then what I would get is 256. So it all works out perfectly. Okay. Finally, I've got a situation where there's a GCF. So in general, and I said this in the lesson from yesterday, and again, if you didn't see the lesson from 318, really go and see this. You should always look to see whether all the terms have something in common. I think we have an intuition that they might, because remember, I also talked about this misconception where people divide everything, so they go like this. And I said how you can't do that because usually when you divide one side, you have to divide the other, but there is no sides here because it's not an equation. So instead, what I said is you need to take that out and you need to do factoring it out. Okay, so notice that 5 goes into 5, 15, and 140. Also note that there's an x, at least one x. Here's x squared, so it's xx. And here's x times x times x. So I can also take out an x. So if I take 5x out of 5x cubed, all I have left is x squared. And you can see if you distributed this, x times x would give you x cubed. 1 times 5 would give you 5. Here I would have 3x because 5 times 3 is 15. And x times x is x squared. And then here, what I have is 28. Because you know how I know this is, when I multiply a number by 10, you add a 0 and divide by 2. When you multiply a number by 5, you add a 0, like you're multiplying by 10, and then you divide by 2. So the net effect is you've only multiplied by 5. Okay? Now I need to see, is the inner part factorable? Can I break that down? The 5x is as broken down as you can get it. And as it turns out, yes, you can. So remember, what I said was, first, you do that. Now, the people who are doing the misconception with the division, you are right that you do want to box out what's remaining. You just don't forget that the GCF has to stick into your, with it through to your final answer, because it is an important part. And again, if you just take out the GCF and don't remember to put it there, what you're left with is a completely different function. And if you graph it, it won't be the same thing. Okay? So now I need two numbers. So we're going to have to multiply to negative 28. And then these boxes here are going to have to add to positive 3. Okay? And since one is a positive, since it's a negative number that we're multiplying to, I know that one of the numbers is positive and one of the numbers is negative. Okay? So as it turns out, we're going to have 7 and negative 4. And what you get is negative 4x plus 7x, right? And 7 minus 4 is 3. So that checks that box, and we're good to go. So I replace it with x plus 7, x minus 4. A lot of people, right, were leaving it and with only the black part and not remembering to put that GCF back. And here's why it matters. Because now I'm going to say, what are the X-intercepts? If you accidentally divided everything up by 5 and x, well, then you'd miss that this means you have to have 0 as an X-intercept. This means you have to have negative 7, and this means 4. So failing to take out the x means you actually miss a really important x-intercept. And at this point in the game, because we haven't had a detailed discussion about these kinds of polynomials, which we call cubic because the biggest power of x is 3, we don't have any intuition about what these graphs are supposed to look like, right? We know the parabola, they either both point up or both point down. But what we know here is actually, if I was going to do a little graph of this, I'll move this down just for like a little bit of enrichment, if you're interested in what a cubic looks like. A cubic, they go in opposite directions, right? You know a line, the end behavior is always opposite, right? One always goes to infinity and one always goes to negative infinity. The same thing is true with a cubic function. So obviously a cubic function is going to look different. So I know I've got, if I'm going to guesstimate here, I know I've got, and I'm just going to try to maintain perspectives here. So I know I've got 4 as an x-intercept, 0 as an x-intercept, and negative 7. So if I was going to draw this, I know it starts down here. Okay, it probably gets up to the half point. It comes through here, and then it goes up something like that. That's what a cubic looks like. And I bet you if you graphed it, you'd see a similar thing. And notice that our x-intercept is also our y-intercept, and that is what happens whenever you have an x out in front, right? Because at the minute I make this x 0, then it's 5 times 0 times 7 times negative 4. And once you have a 0, you know you're going to have a 0, right? The 5 times 0 will be 0. 0 times this will have to be 0. And then 0 times that. So you're going to get 0. Okay, so, but don't forget, this is why we don't just get rid of things, because oftentimes we leave out important information. All right, folks. So I hope you found this video to be helpful. Please make sure you understand at this point really a strong understanding of the factoring, and please make sure you understand the ideas behind using the box method in reverse and some of the really special forms that we've talked about that will really help you save a lot of time and really eliminate a lot of the guesses that might not be right when you do the box. And less guesses is less time, and less time is what you ideally would like to do. Okay, so again, please feel free to reach out to me anytime. You can send me questions at rmoray@miltonps.org, or alternately you could reach out to me over Remind, and our Remind code is course I as in 1 honors. So course IH. All right, folks. So thanks very much for watching. Have a wonderful day. Don't forget to love math.